This project covers our submission for URIC titled Autonomous Cable Traversing Robot for Defect Detection in High Voltage Transmission Lines. My name is Hassan, and with me are my group mates Husain and Kane. This project is supported by the American University of Sharjah through the undergraduate research grant for spring 2026. Award number is UE2647, and the project is supervised by Dr. Ming of the Electrical Engineering Department.
The outline for this includes the project background, our proposed solution, the main engineering standards that we used, our current design progress, and finally, the challenges we faced and our conclusion.
After consulting with engineers within DEWA, we found that current inspection methods rely on ground patrol teams that either use handheld thermal cameras for inspection or just visually inspect conductors from the ground. Another limitation is that although robotic solutions exist to inspect long sections of transmission lines, these robots must move across complicated hardware on the conductors. These robots are also very expensive, with prices reaching $500,000 per unit. After reviewing non-contact defect detection techniques, we found that the most applicable methods for our project are infrared imaging and visual spectrum imaging. These methods allow the robot to inspect components without touching energized cable conductors, while still detecting issues such as hotspots, damaged parts, and visible defects that are missed by the thermal imaging. In terms of the software running on our robot, there are two major players. The first one is the robotics operating system. How ROS works is that different functions can be implemented as separate modules called nodes, and these nodes communicate using what's called topics, where some nodes publish data while others grab this data from the topic. For defect detection, we have decided to utilize YOLO V8, which is an object detection algorithm. The reason behind choosing V8 specifically is because it balances accuracy and efficiency of the detection better than older or newer versions. Additionally, we also found a lot more documentation about its implementation, specifically for transmission line hotspot detection.
Considering these limitations, the primary objective of our project is to develop a robot that can autonomously traverse a dedicated non-live cable while performing real-time defect detection on a transmission line. Our secondary objective is to investigate whether dedicated non-live cable tracks could serve as a supporting infrastructure for future automated inspection and maintenance systems. We propose an autonomous inspection robot that operates on a pair of dedicated non-live cables installed parallel to and above energized transmission line conductors. By introducing dedicated cables, not only do we differentiate ourselves from the market, but we also avoid three main issues. Firstly, we no longer need the robot to cross complicated obstacles on the line itself, simplifying the complexity of the robot design significantly. We also remove direct contact of the robot with live conductors, enhancing safety and lowering the risks of arcs and potential grid failures due to that. Lastly, we create a scalable inspection platform that could support future maintenance and monitoring system upgrades.
This slide shows the full system overview. The robot is divided into sets of components that interact together. The components are responsible for the mobility, sensing, processing, communication, and mechanical protection, and power all onboard equipment.
This diagram here shows how all our components interact. Starting from the power source, the battery provides 11.1 volts through a 30 amp main fuse for protection, then splits into two rails. The 11.1 volt rail feeds directly into the two Pololu motor controllers, which each drive a pair of gear motors. The second rail goes through the buck converter, stepping down to 5 volts to power the Arduino, Jetson, and sensors safely. The Arduino Mega serves as our real-time controller. It handles motor commands and encoder feedback at the low level, communicating with the Jetson via serial. We kept motor control on the Arduino deliberately to offload that timing-critical work from the Jetson, which is reserved entirely for inference. And the Jetson Orin Nano Super sits at the center of our system. It receives visual data from both cameras, runs our YOLO V8 defect detection model, and handles all decision making. The WaveShare Wi-Fi module connects to the Jetson bi-directionally, allowing the operator to receive detection results and send commands remotely.
Moving to the mechanical subsystem. This part of the design handles both robot movement and physical protection of the internal electronics. It is built around three main features. First is EMI shielding. Since the robot operates near high voltage infrastructure, electromagnetic interference can disturb the sensors, controllers, and communication modules. To reduce this risk, the electronics enclosure is lined with copper mesh, forming a Faraday cage structure that helps shield the internal components. Second is the traversing system. The robot uses spring-loaded swing arms to clamp onto the cable from opposite sides. This helps maintain stable contact during movement. The four geared motors provide the driving force, while their integrated encoders give feedback for controlled traversal. Third is water and dust protection. Since the robot is intended for outdoor use, the enclosure is designed with IP67 level protection in mind to protect the electronics from dust, rain, or humidity.
We have two main parts of our software. The simpler part runs on the Arduino, which implements closed-loop control of the motors. The speed and direction set point is controlled by the Jetson U, which communicates with the Arduino through USB. The second part of our software is the defect detection pipeline. Here, data from the thermal camera is acquired by the Jetson using the image acquisition node. The YOLO V8 node picks up the images and then identifies and classifies any defects with bounding boxes and confidence scores. Based on this, an inspection report is generated with images and information about the defects. This report is sent to the inspection team through the communication node.
This is our initial CAD model of the robot. The design uses a two-cable structure with the robot body placed between the cable contact points. This initial CAD model shows the possible placement of the motors, wheels, electronics, battery, and cameras. This helps us visualize how the cables can be placed on the transmission line tower. We also tested the camera field of view in a simulated tower environment. Since the robot moves on a dedicated cable above the other lines, camera placement will be very critical. We need to make sure the cameras can still observe the target components clearly from the robot's positioning, avoiding overlapping and losing line of sight. Here, we tested camera views using 10 to 15mm lenses. The goal was to estimate whether this lens range can cover the region around the conductors and bypass the overlapping of wires. This helps us make better hardware choices before physical testing.
It is also important to highlight the several challenges we encountered during the project. The first challenge was a delay in prototyping. Due to the current situation, the university laboratories were closed for a while, and we had limited access to manufacturing resources and even component availability.
The second and main challenge was limited access to training data. We could not access a ready dataset of transmission line defects from the industry, so the model would not be trained by real operational data. Because of this, we will create our own dataset by simulating and labeling defective images. This will limit the scope of our final prototype.
The third challenge is testing limitations. Due to high risks, we will not recreate real transmission line conditions like high voltage ratings. Despite these issues, we completed the system architecture, selected major components, and developed an initial CAD model. Thank you for watching. These are some of the references we use, and this concludes our presentation.